Hello and welcome. It is the solstice today, and so I thought it would be a great time to answer the question, what is the reason for the season? Now, the metaphysical answer to this, I'm going to leave to you in your own conscience, but we're going to be dealing with the literal reason for the season. So if you know something about orbits, you might be inclined to think that the reason for the seasons is because of the Earth's eccentricity. So the eccentricity describes kind of how much an orbit is not circular. So an eccentricity of 0 is a perfectly circular orbit. Now in an eccentric orbit, you will have a perihelion and an aphelion. So these are the closest and furthest points from the sun during the orbit, as opposed to a circular orbit, which will always be at the exact same distance from the sun. And because we receive our energy from the sun, the distance from the sun is going to impact our weather and our climate. And in fact, the Earth's eccentricity is not 0. It's about 0.0167. So the Earth's orbit is slightly eccentric. It has a perihelion and an aphelion. And the difference between the two is about 5 million kilometers, which is a lot. Maybe not on astronomical scales, but it is a lot. And that energy that we're receiving from the sun, the flux or the insolation, goes as the inverse square of the distance. And so that is to say it goes as 1 over r squared, where r is the distance from the sun. And so small changes in r can have large changes in insolation. And if you do the math, you'd find that the difference between the aphelion and perihelion insolation that the Earth receives is about 6%. That is, at aphelion, it's receiving about 94% of what it receives at perihelion. All right, problem solved. Well, not quite. So there's a major problem with this explanation. Have you spotted it yet? What if I told you that the Earth's aphelion, that is its furthest distance from the sun, was in the beginning of July, and its perihelion was in the beginning of January? Right, so the Earth is at aphelion or perihelion at the same time for the entire Earth. So if this was the reason for the seasons, then the northern and southern hemispheres would have the same seasons, and it would be about to be summer. I wish. But it's not. Not in the northern hemisphere where I'm at. So then, if it's not the eccentricity, what is the answer? It's the Earth's axial tilt. This is also known as the obliquity of the Earth. And basically, this is the angle between the Earth's spin axis and its orbital plane. So the spin axis is not a physical thing, but it is a meaningful thing. So this is basically the axis on which the Earth spins. And this is the reason that north and south and east and west are different, right? The sun is never going to rise in the north. And while we could, arbitrarily change north and south, we can't just arbitrarily switch that with east and west, because they're different concepts because the Earth is rotating. If the Earth wasn't rotating, if it was just a sphere sitting in, space, it wouldn't have any preferred direction. But because it rotates, there's this axis that it rotates on, and that defines a preferred direction for the Earth. So we'll call that the spin axis. But then this is space, there's no up or down, right? So we need something to reference that to in order to make sense of it. And the thing that seems kind of logical is the orbital plane of the Earth. So basically, the Earth is orbiting the sun, and if you kind of drew a line between the Earth and the sun at all times, it would sweep out a plane, and that is what we call the orbital plane of the Earth. So if the Earth has an obliquity of 0, then its spin axis would be exactly perpendicular to the orbital plane. But it doesn't. It has an axial tilt or obliquity of about 23.5 degrees. So that means that it's tilted relative to the orbital plane. Okay, are you following me so far? So what does this have to do with the seasons? Think about it like this. The Earth always has the same axial tilt relative to its orbital plane. So as it goes around the sun, at some point, the spin axis is going to be pointed directly towards the sun, and at some point it's going to be pointed directly away from the sun. And then you'll also have points where it's basically kind of parallel to the sun. So these are what we call the solstices and the equinoxes. Or equini? We'll go with equinoxes. So there's actually two main effects that happen from this. So when the Earth is tilted towards the sun, then we have the summer solstice in the northern hemisphere, and of course the opposite in the southern hemisphere. And this means that we're going to have the longest day of the year. So the northern hemisphere is going to receive the most amount of sunlight at any given latitude that it does all year. And the sunlight is going to be more direct. So the amount of sunlight basically that the Earth absorbs depends on the angle at which the sunlight is coming in. And so if the Earth is tilted towards the sun, the northern hemisphere is going to be receiving more direct sunlight, and so it's going to absorb more of that sunlight. So it's not only going to have a longer day, but the sunlight that it's receiving is going to be more direct and so more easily absorbed by the Earth. And then we get summer. And there's a bit of a delaying factor in here because it takes time for the Earth to warm up. And that's why even though the summer solstice is, June 21st, usually around then, it doesn't really tend to get like super hot summer, like the hottest month of the year, until July and August, because there's a lag to the Earth kind of heating up. And then the opposite happens in December. So in December, now it's the Southern Hemisphere's turn to be pointed directly at the sun to receive that more direct sunlight and have the longer days. Whereas in the Northern Hemisphere, like right now, we're getting the very, very short days with the very long nights, and we're not receiving very direct sunlight during those short days. So it gets cold. I live in Chicago, so it gets cold. Furthermore, this amount of axial tilt that we have is actually responsible for some of these major lines of latitude that you've probably heard of, but you might not have known the significance of. So for example, the tropics of Cancer and Capricorn are actually based on the sun's position in the sky, and they are the northernmost and southernmost latitudes, respectively. The sun can be directly overhead at any point in the year, and that happens at the respective solstice. So today, on the winter solstice, the sun is directly overhead along the line of latitude that is the Tropic of Capricorn, and that is at 23.5 degrees south latitude, and that's not a coincidence. Then on the flip side, we have the polar circles. So the Arctic and Antarctic circles are the southernmost and northernmost latitudes, respectively, that the sun can stay above the horizon for 24 hours at some point during the year. And again, this happens on the solstice. So on the December solstice, which is the summer solstice in the Southern Hemisphere, the Antarctic Circle receives 24 hours of sunlight. This also happens in the Arctic Circle for the summer solstice, and this is, for example, why you hear Alaska called the land of the midnight sun, because in these very long days in the summer, it's above the Arctic Circle in some points, and those points can receive 24 hours of sunlight. And then, of course, on the equator, you're kind of on the balance, and you actually always have, it's basically a permanent equinox on the equator. It's always going to be 12 hours of sunlight and 12 hours of nighttime, just like on an equinox. So on an equinox, the entire Earth, all latitudes, receive equal amounts of sunlight. So it'll be 12 hours a day and 12 hours a night. But that only happens on the equinoxes for any other latitude besides the equator. Also, this axial tilt is responsible for how the sun's position changes in the sky, related to what we just talked about with these different lines of latitude. So if you went out at the exact same time every day, not taking daylight savings into account, so the exact same, kind of physical time every single day, at the exact same time, and took a picture of the sun, and then put that together throughout the year, you'd notice that the position of the sun changes. And it actually makes this shape that kind of looks like a figure 8, and this is called an analemma. And these are really gorgeous. There's a lot of really awesome pictures of them, And the Earth's obliquity of 23.5 degrees there's nothing special about it as far as, I know. There are plenty of other obliquities that we see in our solar system. Some really interesting ones. So Venus has an obliquity of 100 and almost 80 degrees. I forget the exact number, but basically what that means is that it's spinning retrograde. So what that means is when we're talking about spinning, we usually use the right hand rule, right? So if your thumb is pointing along the spin axis, then the direction of spin is where your fingers go. And so if you have an obliquity of 0, it's like this. But Venus has an obliquity of almost 180 degrees, which means its obliquity is like this, which means it's spinning basically backwards. So the sun would rise in the west on Venus. And then you have Uranus, which has an obliquity of close to 90 degrees. So that means that it's basically knocked on its side, and that its spin axis is almost in its orbital plane, which is really cool. So happy solstice to you and yours. I hope you're having a wonderful holiday season, and I hope this helped you learn a little bit more about what the solstice actually is and what's the reason for the season. And I don't know about you, but I think the season calls for some eggnog and some cookies, so I'm gonna go do that. Thanks for watching. I'll see you again soon. Bye.